Well, welcome crew. It has been a long time since we've had a video. This one, we are just really finishing up our 8.1 notes on our introduction to the family of exponential functions. So we already covered the first two pages and then the first example on the third page in class. So I'm going to jump ahead to the next example, which is this carbon 14 problem. So this tells us that carbon 14 decays, that's a key word, at a rate, that's a key word, of 11.4%. So first of all, as a decimal, that would be 0.114. And that happens every 1,000 years. Our job is threefold. The first thing we're supposed to do is write a formula for the quantity Q of a 200 milligram sample that is remaining as a function of time t. So I've got Q as a function of t, where t is measured in the thousands of years. The second thing I'm needing to do is to find out how much of the sample is expected to remain after 3,000 years. And then my third thing is to find how many years it would take for half of the sample to remain. So let's start by defining our variables here. Right? Let's let Q, right, they actually gave that to us, be the quantity of our sample. T is in thousands of years. And what we know beyond this is that we have a rate, right? This is our rate of 0.114. That is a decay rate. And we know that our original amount of samples, so Q of 0, is 200 micrograms, right, which we get from here. Since this substance is decaying at a constant percentage rate, we know that it's an exponential function. So we know that an exponential function takes the form of Q of t equals A, which is our initial amount, so that would be 200, times B. Now, if R is equal to 0.114, then we know that B for decay will equal 1 minus R, which means in this case, B is going to equal 1 minus 0.114, which means that B is going to be what? 0.886. So my value here for B is going to be 0.886. And then we're going to raise that to the T. So that's my first problem, right? Is we have found what Q of T equals. So that's number one. Number two, our job is to find how much of the sample, so we need to find Q when 3,000 years have been passed. So that would be when T equals 3, because T is measured in thousands of years. So if I need to find Q when T is 3, then I'm finding Q of 3, which based on our formula will equal 200 times 0.866 raised to the 3. So I put that in my calculator and I get that Q of 3 will equal 139.101 micrograms, right? So I know that after 3,000 years, I would expect there to be about 139 micrograms of this substance. Okay, the third thing I need to do, is I need to find t when q is half. Well, q starts at 200, so if I take half of 200, I get 100 micrograms. So I'm trying to find what t is, right, when q is 100, so which means I'm going to solve the equation for where 100 equals 200 times 0.866 to the t. And I'm trying to solve that for t. We're going to solve this graphically. So I can graph this as it is, or I can simplify this equation first. If I were to simplify this, I would divide both sides by this 200, and I would get 0.5 equals 0.866 to the t. So I could solve that, but I think I'm actually going to start with this original equation. So I'm going to come up here, and I've got some space up here, and what I'm going to want to do is I'm going to want to graph this. So I'm going to go to my calculator, and I'm going to let y1 equal my exponential equation. So 200 times 0.866 to the, I'll have to use x in my calculator. And then I'm going to let y2 equal 100. So let's move to the calculator on that, and we'll put these in. Let's see if we can bring this down, get this to work. So I've got my equation editor, and you can see from the calculator, I've already put in 200 times 0.866 to the x is y1 and y2 equals 100. So I'm going to graph that. I always like to do a zoom standard. So there's a zoom 6. And you can see that I don't see anything. Well, let's think about that. My initial quantity, which is my y value, is 200, and I'm trying to find when it's 100. So if I look at my window, I only have y's going from -10 to 10. So I'm going to start by changing those y values to match what I've got in this problem. So my quantity is never going to be smaller than 0. Let's take a y min of 0. And then it starts at 200 and then decays, so the maximum I'm going to have is 200. And if I'm going to take y's from 0 to 200, I'm going to go on a scale of 20. Let's try that and see what we see. There's my exponential decay curve, and there's y equals 100. So I want to know where those two intersect. So if I go to my calculation menu, second trace, I'm finding the intersection between two curves. Select that. I'm going to move my cursor to where my curve and my horizontal line intersect. Press enter. Now I'm on the second curve. Press enter, guess. And I get y is 200 when x is 5.7266. Okay. So from here, I would show on my page what I did on my calculator. So we had 0 to 10 for x, we had 0 to 200 for y, and our graph, right, we had, this was y2, y equals 100, and then we had, our curve did something like this. I don't think I quite have that right, but we were looking for this value where these two intersect. Right, so by using the intersection feature, we found that our decay function will equal 100 when t is about 130, when t is about 5.727. Now remember that t is in thousands of years, so this would be after about 5,727 years. Okay, so we did those three things. Let's look at one other example. So we're going to come forward here. It's sort of an interesting problem, true situation actually. On August the 2nd, 1988, a U.S. District Court judge imposed a fine on the city of Yonkers, New York, for defying a federal court order involving housing desegregation. The fine started at $100 for the first day and was to double daily until the city chose to obey the court order. So if we think about this, we have this $100. This is our initial fine. It's doubling daily, right? So this double means to multiply by 2, right? Which means that our growth factor, our B, is going to be 2. That's what we multiply by, right? This is happening daily, so our T is measured in days. Right? Our first question A says, what was the daily percent growth rate of the fine? So we're trying to find the daily percent growth rate, which is to find R. We know that in an exponential growth function, right, that if it's growing, R will equal B minus 1, which for this problem would be 2 minus 1, which is 1. And that's our percentage as a decimal. So to change that as a percentage, we move that decimal over twice. And so we have a growth rate of 100%. If you think about it, that makes sense. If something grows by 100%, it doubles. Right? All of it gets added to it. Our second thing, B, is to find a formula for the fine as a function of t. So let's let the fine be f, and our formula would be that f of t will equal the initial fine, which is 100, times our growth factor, which is 2, raised to the t. So the next question says, if Yonkers waited 30 days before obeying the court order, what would the fine have been? So this is asking me to find, right? So I'm finding what the fine is after 30 days. So I'm finding f of 30, which is going to be 100 times 2 to the 30th. I evaluate that, and this is the number I get. I get 107,374, 182,400, and that is in dollars. So what is that? Over $107 billion, right? Would be the fine if they didn't comply with this order for the first month, right? That's the power of an exponential function.